let me introduce you to this topic that we recently published. You can see it down below. And it's about the phase change material GST326 that we laser switched. I'm going to explain that. And that we investigated with SNOM and KPFM, so Kelvin probe force microscopy. This is a collaboration between our group, so Thomas Taubner group at Aachen, together with Matthias Wuttig, also at Aachen, and Lukas Eng at Dresden. And because Lukas talked about the KPFM quite a lot, I can focus on the SNOM here, which is actually quite nice. I'm going to start with an introduction on phase change materials, because this is a very unusual material class. Phase change materials are materials that can be switched between at least one crystalline and at least one amorphous state back and forth in a non-volatile manner. And that's maybe not interesting by itself, but between these two states, there's a strong contrast in optical and electrical properties. So as you can see here, for example, the resistance changes from a high value in the amorphous phase to a lower value in the crystalline phase, and then back and forth. And also the optical properties change quite a lot. And this gives us a lot of applications, for example, electrical and optical memory applications or tunable optics, especially non-volatile tunable optics, which is why there's a lot of work at the moment on metasurfaces. And why is this material so useful for that? That's based on the dielectric function. If we compare the real part here of the dielectric function in the amorphous phase, we have a relatively high index of refraction of 3.5, but if we go to the crystalline state, we crystallize it, this changes very strongly to a value of 36, so here in the infrared region. And this is due to a special bonding mechanism called metavalent bonding. If you are interested in this topic, I can recommend this article by Matthias Wuttig, which goes into detail, but it's basically a contribution of the electronic background at higher frequencies that strongly changes between the two phases. And this was used for several applications. So the Sheludev group proposed, for example, these written surfaces with resonators, but in the order of the wavelengths of light, so diffraction limited. But if you use a phonon resonant substrate with surface phonon polaritons, for example, you can also go deeply sub-wavelength, also very interesting. And if you make resonators out of the material, you can switch them directly. So point-by-point addressing. And the interesting part is that you can use a laser to switch them. So you heat the material locally with the laser, it will be switched. And this allows you to do directly writing or tuning of these surfaces. There's going to be talk in the next session on this, so I'm not going to go too much into detail. But what Peining Li also did in our group, so in the same paper, is he looked at laser-written spots of this material. And because there's a strong change in dielectric function, as we said, if you write a spot, you see a contrast in the SNOM. So this is a near-field optical image. And then you can erase them again by going back to the first phase, basically, and then the contrast disappears. Then you can look at cyclability, which is, of course, very important if you want to make a device, and also motivation. But to understand the cyclability, let's look at the switching process maybe in a bit more detail. So we start with an S-deposited amorphous phase, for example, by sputter coating. We heat this up with a laser beam above the glass transition temperature. We get crystallization going on. We cool it back down, and it's crystallized. And then if we want to re-amorphize this material, we have to go above the melting temperature, so really get a melt, and then quench this rapidly to get a melt-quenched amorphous phase. And this one we can crystallize then again, so recrystallized. And the point is, these two phases, even though they are both amorphous, they are known to be not exactly the same, so there's differences in nucleation seed concentrations, and also the crystalline states show, for example, different grain structures. So this is a question about local conductivity as well. I told you that there's a contrast in electrical properties, so in local conductivity. And if we look at the dielectric function again and we add the imaginary part to this, you can see that in the amorphous phase there are basically no electrons or no conductivity. There's no Drude response at low frequencies. But in the crystalline state, we get the typical Drude response in the imaginary part. So if we think that these two states, these two crystalline states could be different, we should be able to see this in the dielectric function, but because it's local, it's directly written and it's very small, it's difficult to measure this on the far field, for example. And that's why we want to use SNOM to investigate local changes to dielectric function due to charge carriers. And because the sensitivity is highest at lower frequencies, it makes sense to do this at low frequencies. So we went to the free electron laser, which is the collaboration with Lucas Eng, and we also compared this to mid-infrared measurements, of course. So to give you an overview, we investigated all these 4 states basically in one sample, and wanted to get the local conductivity from SNOM measurements, and we also did the KPFM measurements at the same time, as Lucas already described. Now, to show you how the sample is built, basically, just to make it understandable, we start with an S-deposited amorphous layer, which you see here from the top. Then we write a crystalline line into this with the laser spot. Then we add some re-amorphized spots to it, which are slightly offset of the line here, where it's basically melt-quenched. And then the last few spots are recrystallized. And then we investigated this with SNOM and KPFM, as I said, and looked especially at the re-amorphized spot and the recrystallized spot. The re-amorphized spot is in the paper because there's not enough time. But I'm going to look at the recrystallized spots here with you and to see what actually happens there. So if we look at these images that we recorded, which is an AFM image, a SNOM image, and KPFM image, all at the same time in situ, first you see a change in topography, right? So there's some topography going on there. That's because there's a density change between crystalline and amorphous state. So the crystallization leads to a slightly reduced height in the material. Then there's a strong contrast in the SNOM signal, which we already saw before, between the crystalline and the amorphous environment. And then, interestingly, the KPFM signal shows us a region outside here, which is not visible in SNOM, and which is basically the leftover of this melt-quenched spot that we saw before. So if you look at line profiles across the spot, we start with the amorphous region outside of this line. Then we have this leftover melt-quenched state, basically outside of the line that we can identify in KPFM. So this is why the combination was very powerful. Then we get our recrystallized state, which is very bright in the SNOM at this frequency. So this is in the far infrared. And then we get the leftover of the crystalline line, which has a different level. And then we go back to the amorphous. So combining these 2 methods in situ allows us to actually identify all 4 phases within one single scan. So this is quite nice. And also, if you look at these levels here, there's the contrast difference of 80% roughly that we expect could be due to changes in the local conductivity, right? This is what I explained at the beginning. So we, of course, compared this to the mid-infrared measurement. This is just a quick line profile here. And there you don't see this contrast of 80%. And this is because in the far infrared, we are more sensitive to the charge carriers than in the mid-infrared. But as is usual in SNOM, if you have a contrast, it's difficult to explain it with a dielectric function, so you really need to check what this actually is. So we did some finite dipole modeling of this with dielectric functions. I'll show you this in a second, but to not keep you in suspense, so the result is also that at this far infrared wavelength, we get this 80% contrast, and this disappears in the mid-infrared region. So this nicely confirms our measurements that we did. And where does this contrast come from? This is a bit unusual, so I'm going to go into a bit of detail here. You remember the dielectric function of the crystalline state. We have this Drude contribution in the imaginary part. But if you know Drude contributions, you know that the real part should also go down to, for example, negative values. This is due to the formula where you have this background going on, which is very high in the phase change materials, and then you have this real part of the plasma frequency and the damping. And in these materials, the damping is quite high. So this means that you don't have this divergence of the real part at low frequencies towards 0 frequency, but you just get a finite contribution. And because the damping is actually higher than the plasma frequency, for example, this means that the contribution is very small. So if we look at this in calculations of the dielectric function, increasing the charge carrier density by 1 order of magnitude leads to barely a change in the real part, and a large change in the imaginary part, because this still diverges due to this omega there. So using this as the basis for our SNOM simulations, we can look at the coupling function. Many of you probably know this. This tells us what SNOM signal could we expect, so here the optical amplitude, for different dielectric functions. So the real part is the x-axis here, and the imaginary part encoded in the curves. And you see here some things that are typically known. So there's this so-called linear regime where the contrast follows or the signal follows the dielectric function, where all the polymers and the biological materials and so on are. There's the near-field resonance for slightly negative values between -1 and -10. And then there's the region where we are, right? So this is very high real parts of the dielectric function. So actually, there's not a lot of change going to be expected there. And if we zoom in, we see the real part, it drops by 1, roughly from 36 to 35. And the imaginary part increases a lot with adding charge carrier densities. So we're expecting to follow this signal, basically. And then this is what happened. And to give you the conclusion, we investigated these 4 states of optically switched GST on the nanoscale with SNOM and KPFM. And SNOM is generally able to differentiate crystalline and amorphous very well, also in the mid-infrared, and especially well in the far infrared, and there also these different charge carrier concentrations. And KPFM is able to differentiate between before and after melt quenching, and the combination is able to allow us to distinguish all 4 states. And then combining the 2 frequency regions, far and mid-infrared, actually allows us to identify this charge carrier contribution, which could be explained by a rise in charge carrier concentration of 1 order of magnitude. So we expect not a large influence of this effect on mid-infrared applications. We talked about metasurfaces and so on. But if we think about terahertz applications, this could become very, very relevant. So what we are going to look at next probably is several switching cycles of this. So what happens if we switch it again? Is this just because it's from the S-deposited state, or does this change every time? We are going to try a large area reamorphization, which is still a bit difficult to really do transport measurements and confirm our electronic properties that we extracted there. Someone could try cryo-SNOM experiments on this to see if the mobility changes, the damping changes. Maybe we can separate this mobility and charge carrier concentration influence. We are going to look at the KPFM origin in more detail because this is unclear yet where this comes from, this change during the melt quenching, and then extend this to other PCMs such as indium antimonitelluride, which Konstantin will probably talk about. So thank you for your attention. Thanks to all the partners, and I'm open for questions.